All right, I think it's time to start. And before I go to the quiz, the Top Hat quiz we did on Friday, I wanted to ask you, were you able to listen to the recorded lecture?
Yes.
Okay.
Yes.
And also you were able to have access to the material that I covered, I mean, as a separate file. You saw that I had attached it below the in Canvas. You will always see the files attached by day below the topic. Did you try to see that? The file, the PDF file?
I didn't check that.
I'm checking right now. Hold on.
Yeah, could you check and see whether you can see it?
Yeah, it looks like it's all here.
Okay, perfect. So what I would suggest is that it's good that you listen to the lecture, but the file is exactly what I followed, and that's what I do right now. In fact, nowadays I put everything that I cover in lecture with even more material. And then if I add material to this file as we go through the lecture, then I copy the whole thing and I put it. So you don't only have the recording, but also you have the file underneath it. And that's going to be useful. So going back, first of all, we are not going to have an exercise today because I would like to cover some material and then we are not going to have enough to give you something meaningful. But I wanted to say on the quiz, so we did very well. I mean, 77% provided a correct response. But what I wanted to say is that there were a few students who, as you can see here, scored or identified the wrong answers. And what I would suggest is that you need to go back and look at my notes. And that's why I asked whether you have access to it. Because the answer, as you saw that most of your colleagues responded correctly, it is important that you go, for those of you who have seen that you made a mistake, go and check and make sure that you understand the correct answers, because these are very fundamental things and you're gonna have to know them all along. I mean, these are extremely basic concepts that you will need to make sure that you are familiar with, because we built on those to move forward. Okay, so that much about this one, this topic. And then before we start today with, we are starting today practically trying to put everything together about low noise amplifiers. Obviously, you've seen it as part of the homework and the matching circuits, that we know more or less how to design the matching circuits for a low noise amplifier if it is in unconditional stability. Obviously, that does not happen all the time. And so this week, we are going to be able to just put the whole material together about low noise amplifiers, and then we'll talk about the gains and what types of gains we have and so forth. Everything that we have done so far, it becomes important here. For example, everything, and that's what I've been telling you all along, everything that we've learned about network matrices becomes important, because as we discussed with the low noise amplifiers, we characterize them in the form of a scattering matrix, not of an ABCD matrix, but a scattering matrix. So that becomes important. Anything that we've learned about matching networks becomes important. All right. So all of this material is important, creates the foundation, which now we're going to be able to learn about those. Before we start though the lecture, I wanted to say that you have a new homework number 9, which you should be able to access because I just released it today. you're going to have until the following Monday, not today, I mean a week from today at night to submit it. And it's just on filter design. All right, everything that we've done so far on filters, I'm asking you to do a bandpass filter practically and do it in microstrip form. So look at that. I hope that we have covered, I think, I'm 100% confident that we have covered all of the material you need to do for this, you need to have for this homework. I also released the project, which is going to be due on November 1st at night, Sunday late. And this one now is to go back into your project that you have now identified from previous work, the types of receivers you're going to use. Then now you will have in the next 2 weeks to very specifically identify the characteristics of the filter or filters you have in your system and then design them. And so this is very important because if this design is not done well, if your specs are not developed well, your receiver is not going to work at the end. So this is out there for you also. So now you will be able to do all of your filter designs. And then the next step will be to do the low noise amplifiers and so forth. So you will see also at the end of the project that I have put an updated version of our outline with the various steps, what we've done so far, where you've been, and what we have to do next. What we are not going to do is to, probably we're not going to have time, I believe, to do oscillator design, which is important in mixers. So mixers will just assume that it's a piece, it's like it's a component that somehow we don't have to worry about it. Somebody's going to give it to us. It's going to work ideally in your project, because oscillators and design of oscillators is a whole big thing. And we're not going to have enough time to do it well. And then if we do it, we are going to do it at the cost of understanding some other important topics. So that's what I wanted to give you as an update of where we are today. And unless you have any particular comments, I would like to move to the lecture. But I will pause for a few seconds, like 30 seconds, to hear whether you have any comments or suggestions or any questions.
Have you assigned like the, Dr. Katehi, have you assigned like the makeup assignment yet?
Not yet, because I have received only one person who has responded to me.
For what?
I have, whether you want to take the you remember I have asked 2 weeks ago, I asked people to send me a note of who wants to do the makeup assignment. The makeup assignment and why. The makeup assignment is not going to be for everyone, because if I give a makeup assignment to everybody, then I will have to give another makeup assignment for those who deserve to have an additional opportunity because they missed whatever parts of our class, and they, for valid reasons, and they want to make up for it. So, okay.
Professor, what would be valid reasons to take the makeup?
Valid, I'll tell you. Valid reasons will be that you had another conflict with another class, either an exam or like something else, something valid, that forbid you from doing the specific homework or doing participating in a midterm or whatever, something like that. Whether that you got sick, for example, and then you were not able to participate in something. A valid reason is not that you missed points in your homework because you misunderstood something. And the reason it's not that is because then the whole class will have something like this. So I will follow the descriptions of what is appropriate for a makeup assignment as the university has published them, all right? So I will use those. If you want to know specifically what those are, they are listed on the website. And in fact, if you go into my, I have included also on eCampus a syllabus at in brief, something like that is called. And then at the end of that, I have all of the university processes that you need to be aware of. And then in addition to that, also the reasons for a makeup assignment. Now, if you have a reason and you are not sure of whether this reason is valid or not, you can still talk to me and we have a discussion and I will tell you whether I will accept it or not, okay? But unless I know, I got only for one person who needed very few points. Well, that is not good enough to develop a whole full assignment because I'm gonna develop it from scratch. I don't copy from other assignments. Okay, so I only got one. And unless I receive a little more, because for one person, I can give this individual something, you know, separately. I don't need to create something for the whole class. So let's work this week. By Wednesday, I want those who need to take a makeup assignment to send me an email with how many points you have missed and why. I need to know the points too to make up the makeup assignment. Okay? Is that clear? By this Wednesday. Okay,
Clear.
thank you. All right,
And
perfect.
one more thing, I think you still haven't graded my midterm yet.
Yes, you're right. You're absolutely correct. I apologize. I will do that. In fact, immediately after my office hours.
Okay, okay.
Yeah, you're right.
Thank
Okay, you're welcome. All right, let me start now. So if you remember, this is in fact how, if we have a low noise amplifier, okay, this is how we start with. This is exactly the kind of circuit we will be looking at, where what you see here at the center, this one is your transistor with whatever bias networks this transistor has been designed. And if you remember from the homework and the project, that usually we know the scattering parameters and they give those scattering parameters to us versus different bias points, okay? And so we have these tables. Anyone who designs a transistor that performs at high frequencies, they will have those specs available. And they are extensive. It's not just there are pages of specs, but the most useful part for us is the frequency, of course, where this transistor has been designed to work at, but also because they will tell you in the beginning that this has been designed for that kind of frequency band. And then you know that in that frequency band, if you don't go too close to the edges of the band, that your transistor is performing well. Now, then you go a little further down and you will see that they have these extensive tables where they have frequency on the left, and on the top of its table, they will have the DC bias points, all right? How much is your IC, the current at the collector, whatever. How much is your temperature and all of this. And then, or how much is your DC or the VCE and so forth. They will have it there. And then they will give you all the scattering parameters for that. And then we also, if you remember, we use some formulas that for K and D or delta, how many, there are two parameters which are important. And these two parameters are telling us whether this transistor is in stability. All right. And as a matter of fact, we were designing it so it was unconditionally stable. And what that means, as we will learn also here, is that unconditionally stable means that whatever the load is, here the load is Isabel, if you see it. Is this Isabel. Whatever the load is, or whatever Isabel is, this transistor is not going to oscillate. That's what it means, unconditionally stable. Now, there are many other great transistors, however, where they are stable, but for some very specific ranges of values, not just one value of ZL and one value of ZS, but for ranges of values. So for example, if you have a space where different ZLs can be selected from and another space where different ZS can be selected from, then you find regions, all right? Not just specific values, but regions where the transistor is stable. And that is called conditional stability. And then we will learn how to identify those regions where we can match or design the matching networks so we create a good low noise amplifier, all right? But coming back to the fundamentals, to be able to communicate with other designers about how well your transistor has been designed, there are a number of interesting definitions and people are using them. So one is the power gain that you see here. The power gain is nothing else, but if you take this up here and you assume that P sub L is, let me write it as a matter of fact, that P sub L is the power absorbed by the load, and P sub in is the power that is entering the transistor structure. In this particular case, we show a 2-port, all right? Then the ratio of these two powers is called the gain, the power gain. And in fact, you can use that for any other 2-port. These are good for any other 2-port representations, but they are most used, obviously, as you can imagine, in power amplifier designs. So the power gain. Why are they not used for anything else, you think?
Dr. Kateki?
Yes.
So the Pn equals Vn squared over Rn, right?
P in, if it's in real power, then it's going to be the 1/2 the magnitude of V in to the second power divided by the magnitude of Z in.
Magnitude? It
Yeah,
should
I
be the
mean,
real
you know,
part.
the magnitude, I mean, square root of that. Or in reality, if you want to find it as a real part, the real part of this. All right, by R in. Let me write it down. Okay, I will write it down for a moment so we don't have any.
Why we multiply it with 1/2?
Because if you look at the book, there are different books that have the 1/2 or they don't. And that is one complication of how the whole thing started. Let me see. There. Okay, in our book, let me just say this much and I will explain. So P in, that's what you asked me, is gonna be 1/2 V in real of Z in, all right? And I just wanna say that in fact, the reason I said that, but I will have to be careful here. Let me erase that and do it from the beginning. I would like to divide it, to write the formula. So the formula is B in, V in, I in complex conjugate, okay? Do you agree with that? The question is why we have 1/2. Is that right?
Right.
Okay. If you go to the book and you see how P in has been developed, the formula, if your V in and I in that we have in there show maximum values, all right, it will be complex, but if the coefficient in front of the complex, so for example, your I sub-in will be in the general case, this one, with some kind of phase, all right? And your V in will be this one, also with some kind of phase. And this phase, this is 4 prime. And there is the relationship between the two is that V in equals Z in times I in, okay? So depending on the Z in, if your Z in is complex, of course, the phase of I in and V in will be different. If your Z in is real, the phases will be the same. Now we go, if your I in, so in this one, the condition is, as an, oh no, the asterisk is not a good idea. So the condition in writing this formula is that V in what the way I have written it, and I in indicate maximum values, max, and not RMS. All right. There are some other publications and books where
I see.
those will be RMS values, and then the 1/2 goes away.
Yeah, the RMS value for both V and I are 1 over square root of 2. So
exactly.
yeah, they multiply together.
Yes.
Just 1.
Yes.
half.
All right. So this, and then you remember that. So if you have a book or you look at some that does not show, so I'm going to write the other one, and then in a different color so you see it. And then P in is V in I in complex conjugate if V in and I in are RMS values. And if you remember, V in RMS is V in max divided by square root of 2.
Yes, but I also remember that in the exam it's 1/8.
That's different. So we're not going to go to the exam right now, okay? Because I have to solve a different problem, but we can do it during office hours. If you come to office hours, we'll do it there, okay?
Okay.
So let me, now, you asked me another question about P. Then you plug in, according to that, to here. I want to finish that, all right? So if we close that here as a note, and then we will have that P in, if I continue with the above, will be 1/2 V in complex conjugate, sorry, to the second. And then underneath it, what is it going to be? Z in what?
It should be Rn. Because
No,
that's only the real parts.
Well, let's see that. Okay. Do you agree that it's going to be like this?
I think it should be real parts.
Forget about the real part for a moment. Do you agree that I in complex conjugate is V in complex conjugate divided by Z in complex conjugate? Yes or no?
No, it should be Oh, it should. Yes, yes, yes.
Okay. If you do that and you plug in, that's what you get here. Now, let's see what happens if Z in, and in fact, I want to thank you for this because it's a minor detail, but it's an important one, and a number of the students make a problem, make a mistake. So let's assume, how I'm going to do this. Let me, in fact, start. Assume here, be clean, assume that Z in is R in plus J X in. Okay, we make this assumption, it's complex number. Then what happens? Z in is what? R in minus JX in. Do you agree? Huh?
Yes.
Okay, where R in and X in are real values. All right, now, how much is one if, okay, let me assume that I want to find the real power of this entity. Let's assume that I want to find that. Then I'm looking at the real value of 1/2 magnitude of V in squared divided by Z in complex conjugate. What is going to be then? Then this is going to be 1/2. This is real. It's a scalar, real number. And then it's real of 1/Z in complex conjugate. How much is that? That's the question that I have now. What do you think? Who can tell me how much is this real of the inverse?
Should it be the real of P in or R in?
Think first.
Well,
Square root of R in.
Okay, what am I going to do to find it? Think before you say. Unless you have seen this before and you can help me immediately. What would you do next?
Multiply the denominator and the numerator by the complex conjugate. So R n plus
Yes, you're absolutely correct, but your voice is very, I cannot hear your voice very well. So,
sorry about that, but my mic's not working the best right now.
okay, fine. Now I got it. Yes, you're absolutely correct. Do you agree that this is what I have? I'm sorry. I hear somebody should put a mute so there is a reflection. There are signals reflected. Now you can see what reflections can do. Okay. How much is that? Did you see what I got? So what is the learning? What is the outcome of this? That the real of the inverse of a complex number is not the real part of the complex. Unless the number, of course, is real. I mean, if the number is complex, that is what you have to keep in mind. Okay?
It should be 1/Rn.
Where?
I mean, the real part
that
of
one.
1/.
Yes, got it. Okay, don't pay attention to that. Look at the other thing.
So that
Focus
one,
on that.
okay. The real part of 1 over Rn minus Jn equals, yeah, 1 over the square root of Rn squared. 1 over square root of Rn squared plus Xn squared times e to the J inverse tangent of X minus Xn over Rn.
What are you talking about?
Yeah, the algebra.
Yeah, but look at this. Why do you want to go and find the phase?
So we usually use I mean, we usually use the form of,
Don't
we
do
usually
it
use
that
polar
way.
form, right?
Yeah, but
To
why would you
do-
want to go to the polar form? It's like you go from here to Houston through New York. Why do you want to do that?
I mean, like, usually we do multiplications and divisions using polar form and do
No,
addition and
this is
subtraction.
only what the formula says. No, in engineering, you do what is the simplest.
Okay.
If you don't try, I mean, let me guys tell you something, and girls, you try to learn how to do the simplest possible thing, because the best solutions and the most elegant solutions are the simplest ones. If you follow recipes, you will never get anything right. That's why I don't like recipes myself, because it's very hard to remember them and they will never give you anything good. We use the recipes early to understand the concepts. The moment you understand the concepts, you connect the concepts with physics whenever you have to, then you don't follow a recipe. You don't follow a recipe. The recipe is like you cook a food. When you cook a dish for the first time, you read everything that they tell you underneath it. Are you going to get the best dish possible? Rarely. You're going to do something that is edible, but it's not going to be your best thing. Usually your best recipes are the ones that come out of experience, and very few chefs will read the book and do a good dish for you. Okay, it's only for the beginning. So the same thing applies in engineering. Do the simplest thing possible in every step to be able to do it right and to do it well. So this is the one I would do. This is always what you're going to do in this particular case. You're not going to go from rectangular to phase to polar form unless you have to. If you see, and now let me get that, going back to our topic. If you see in scattering matrices, especially in many of those pages that provide descriptions about the transistors, they will give you scattering form either in rectangular or in polar form. And according to what you have to do after that, you will have to either leave it in polar form, because it is true that if you already have it in polar form and you have to multiply or divide, it's a lot easier. But if you have it in rectangular form, as they do in some other cases or on other tables, then don't go immediately to change it to polar form unless you have to. All right, so in this particular case, it did not pay to go to polar form and try to find that, but it was easier to do it the way we did. Okay, so now you got power gain. Why? My question was, and nobody answered it. Why do we not use power gain for passive structures?
It doesn't make sense to talk about power gain for things that are not amplifiers.
Exactly. So what is the maximum value of the power gain if you have a passive structure?
1.
1. In this particular case, if I have a very well-designed matching network without losses in there, so transmission line, and assume you have no loss transmission line, practically, your power gain is going to be 1. Okay, now let's go to the next one, which is the available gain. What is the available gain? You remember, we will see it again, but we are going to also, we did it also, we saw that in the homework and in the project. There are different designs when it comes into a low noise amplifier. You can design for maximum gain, or you can design for maximum efficiency in terms of noise, all right? Or minimum noise, minimum noise. So the two designs are slightly different. Maximum gain, which is what we do most of the time, because we want our low noise amplifier to give us, well, we want really maximum gain and we really want low noise, but depending on the implementation, depending at what stage of your receiver, your amplifier, your low noise amplifier is, if it's at the very front of the receiver, you have to design for minimum noise, for the best signal to noise ratio. Why is that? Because your signal already comes with a lot of noise. The last thing you want to do is to try to amplify it and add more noise to it. So I can do with less gain in my low noise amplifier, which is at the front, just after the antenna and the very first filter, but I need very low noise. I will do one particular design for that low noise amplifier. But then as I go inside my network, meaning the receiver, then where my signal has already been cleaned, going through multiple filters, and has already been amplified by a low noise amplifier. And now I would like still to have a low noise amplifier because my signal is still at the high frequency. If I place another low noise amplifier, this time I'm gonna go for maximum gain. All right, because my signal is not that sensitive to losses, to noise anymore, and losses from noise. Okay, so they're slightly different designs. But if you go, as you can see, we talked about maximum available gain. And when do you get maximum available gain? At your load. Do you remember what we did to get the maximum gain? What did we do? We had to place two matching networks. We had to place one matching network here and another matching network here. And I can, in fact, we had to place one here and another there to do what? To achieve conjugate matching. Remember that? Because if your gamma in is equal to the complex conjugate of gamma S, and your gamma out is equal to the complex conjugate of gamma L, all right? And we have to only achieve that through a matching network, then we get the maximum available gain at the load. And why can we not achieve this with any other way but with matching networks in these two locations that I have shown you? Because gamma in and gamma out are controlled by the transistor and by the bias networks. And gamma L and gamma S are controlled by your load and by your source. So your load is going to come from a different component that was designed by somebody else. It's given to you. Your source is going to be given to you. And your transistor is going to be given to you. So what are you going to do? You're not going to be able to put all of these heterogeneous pieces together and achieve conjugate matching without doing anything. So the one thing as a designer you have to do is to put this matching network so you achieve this conjugate matching and you get maximum power. All right. So there is another interesting gain that is called the transducer gain, which is whatever P sub L goes to the load divided by the maximum average by the source. This is the optimal gain, if you like. The transducer power gain is practically the one that tells you how much, what is the optimal design your optimal design can achieve, because your source gives you this much, your load is what it is, and then everything in between is what is in some ways under your control, so you can maximize the transducer gain. All right, so these are the two important things. Now, before I go down, and we need to, obviously, as a designer of a receiver, you will need to have, for a given, look at these expressions, you need for a given transistor, for a given load, and for a given source, to be able to calculate your gains. Whatever gain is most of the maximum gain, or just the gain, or the transducer gain. And these expressions, if you are to do them the traditional way that we normally do, are very complex. So at that point, I decided that I wanted to introduce to you something which I thought maybe it was not important, but I think it's gonna become important. I think I decided it was important to introduce it to you so you can see how those are calculated. And this is what I call the flow graphs for the signal flow graphs for a two-port network. And these are also, from an engineering point of view, it's like the Smith chart. These are very useful tools for easy calculations, all right? So for you as a designer, not to run all the time to MATLAB and do things. Okay, any questions before I then introduce those? So we will stop at the definition of the transducer gain. We'll go to signal flow graphs, and then we'll come back to see how using signal flow graphs we can get those expressions, which in fact, in reality, to get them through traditional forms, using scattering matrices and going from there to ABCD matrix, and all of this is, it's very complex. Any questions before I leave this part?
Could you please stay here for about 1 minute?
1 minute is a long time. I'm sorry. Okay, yes, I will, until I need to get also. Can you take a quick copy on your phone with this, or your machine?
Yes, I've taken a screen.